Howdy, and welcome to a probably very sketchy read-through. I just stumbled across this. It sounds very interesting because, microscoping stuff is fun. 6 hours ago, they posted technology enables conversion of mobile phone cameras into high-resolution microscopes. I made a quick read-through for myself and figured out that there are many complicated words. And this might be more humorous, or I try to keep it on the humorous side because there are so many complicated words. And I also saw that as a challenge for my English. But anyway, researchers in Singapore have developed the world's smallest LED light-emitting diode that enables the conversion of existing mobile phone cameras into high-resolution microscopes. Smaller than the wavelength of light, the new LED was used to build the world's smallest holographic microscope, paving the way for existing cameras in everyday devices such as mobile phones to be converted into microscopes via only modifications to the silicon chip and software. This technology also represents a significant step forward in the miniaturization of diagnostics for indoor farmers and sustainable agriculture. And geologists, for example. And random dudes like me who are interested in geology. Anyway, this breakthrough was supplemented by the researchers' development of a revolutionary neural networking algorithm that is able to reconstruct objects measured by the holographic microscope, thus enabling enhanced examination of microscopic objects such as cells and bacteria without the need for bulky conventional microscopes or additional optics. Note, this was one sentence. The research also paves the way for a major advancement in photonics, the building of a powerful on-chip emitter that is smaller than a micrometer, which has long been a challenge in the field. The light in most photonic chips originates from off-chip sources, which leads to low overall energy efficiency and fundamentally limits the scalability of these chips. To address these issues, researchers have developed on-chip emitters using various materials such as rare earth doped glass, GON-SI, and heterogeneously integrated 3 to 4 materials. While emitters based on the materials have shown promising device performance, integrating their fabrication process into standard complementary metal oxide semiconductor platforms remains challenging. While silicon has shown potential as a candidate material for nanoscale and individually controllable emitters, silicon emitters suffer from low quantum efficiency because of the indirect band gap. And this fundamental advantage combined with the limitations set by the available materials and fabrication tools has hindered the realization of small native silicon emitter in CMOS. In a recently published Nature Communications paper titled Sub-Wavelengths Silicon LED integrated in a SCMOS platform, smart researchers described their development of the smallest reported silicon emitter with a light intensity comparable to of the state-of-the-art silicon emitters with much larger emissions area. In a related breakthrough, smart researchers also unveiled their construction of a novel untrained deep neural network architecture capable of reconstructing images from a holographic microscope in the paper titled Simultaneous Spectral Recovery and CMOS Micro-LED Holography with an Untrained Deep Neural Network, recently published in the journal Optica. The novel lead developed by smart researchers is a CMOS integrated sub-wavelength scale LED at room temperature exhibiting a high spatial intensity. Intensity 102 plus or minus 48 microwatt per square centimeter. What? Is it a what? Big W? I don't know. Anyway, then processing the smallest emission area 0.09 plus or 4 micrometers, square meters. Anyway, among all known SIE emitters in scientific literature. In order to demonstrate the potential practical application, the researchers then integrated this LED into an inline centimeter scale, all silicon holographic microscope requiring no lens or pinhole, integral to a field known as lensless holography. Holography setup, incident spherical wave, incident and scattered light. Spherical wave. Anyway, the spherical wave. No, anyway. A commonly faced obstacle in lensless holography is computational reconstruction of the imaged object. Traditional reconstruction methods require detailed knowledge of the experiment setup for accurate reconstruction and are sensitive to difficult to control variables such as optical aberrations, the presence of noise, and the twin image problem. The research team also developed a deep neural network architecture to improve the quality of image reconstruction. Deep neural network architecture. Some AI stuff, I guess. This novel untrained deep neural network incorporates total variation regularization for increased contrast and takes into account the wide spectral bandwidth of the source. Unlike traditional methods of computational reconstruction that require training data, this neural data network eliminates the need for training by embedding a physics model within the algorithm. In addition, the holographic image reconstruction, the neural network also offers blind source spectrum recovery from a single diffracted intensity pattern, which marks a groundbreaking departure from all previous supervised learning techniques. Yeah, it has an open mind. The untrained neural network demonstrated. The open-minded neural network demonstrated in this study allows researchers to use novel light sources without prior knowledge of the source spectrum or beam profile, such as the novel and smallest known silicon LED described above, fabricated via a fully commercial, unmodified bulk CMOS microelectronics. The researchers envision that this synergetic combination of CMOS micro LEDs and the neural network can be used in other computational imaging applications, such as compact microscope for live cell tracking or spectroscopic imaging of biological tissues, such as living plants. I think there's some talk on, about plants, the electricity in plants, they're communicating, mushrooms are chatting after rainfall and all this kind of stuff. I bet the trees are talking too, not only the shrooms. But anyway, this work also demonstrates the feasibility of next generation on-chip imaging in systems. Already, inline holography microscopes have been employed for a variety of applications, including particle tracking, environmental monitoring, biological sample imaging, and metrology. Metrology. Yeah, I don't know what meteorology is. Or is it meteorology? I don't know. Further applications include arraying these LEDs and CMOS to generate programmable, coherent illumination for more complex systems in the future. Ik-Sung Kang, lead author of the Optica paper and research assistant at MIT, at the time of this research said, "Our breakthrough represents a proof of concept that could be hugely impactful for numerous applications requiring the use of micro LEDs. For instance, this LED could be combined into an array for higher levels of illumination needed for larger scale applications. In addition, due to the low cost and scalability of microelectronics CMOS processes, this can be done without increasing the system's complexity, cost, or form factor. This enables us to convert with relative ease a mobile phone camera into a holographic microscope of this type." Yes, MIT, if you are listening, I really would be pleased. If you have a phone with this kind of application, you could send me. I really have many things I would like to watch at. Microscopically. Stones and stuff, Yeah. This would be very cool to have this kind of a tool on the phone. Imagine that. Now, as I figured out to put some stones in the microwave, I could take a sample of the stone and watch it with a microscope, make an analysis, put it in the microwave and make an analysis again. And I could compare them. And I really wouldn't know what we are looking at. I could come up with some conclusions about stuff. But anyway, now I just remembered one thing. This enables us to convert with relative ease a mobile phone camera into a holographic microscope of this type. Whoa! Furthermore, controlled electronics and even bigger, even the imager could be integrated into the same chip by exploiting the available electronics in the process, thus creating an all-in-one micro LED that could be transformative for the field. Yeah. This is what I wish for next Christmas. On top of its immense potential in lensless holography, our new LED has a wide range of other possible applications because its wavelength is within the minimum absorption window of biological tissues. Together with its high intensity and nanoscale emission area, our LED could be ideal for bioimaging and biosensing applications, including near-field microscopy and implantable CMOS devices. Yeah, this sounds creepy. Implantable. Added Rajiv Ram, principal investigator at Smart Camp and Distap, professor of electrical engineering at MIT, and co-author of both papers. Also, it is possible to integrate this LED with on-chip photodetectors, and it could then find further applications in on-chip communication, NIR proximity sensing, and on-wafer testing of photonics. Yes, there were many, many complicated words in that. But the thing I just remembered before is that some time ago I have been in Outokumpu. And I've been talking about this Outokumpu place many times. It's in my first paper. Mentioned several times. And there is a copper mine. And Outokumpu, if it translated, is like strange hill or odd hill. Or bump, in a way. And the copper mine. That's a picture I took some time ago from the Outokumpu copper mine. And that's really somehow at the bottom, there's like those train tracks going there. And I really wondered about this red color. There's like this red stuff everywhere. And also, of course, this greenish, yellowish. This is maybe not the best quality ore, I don't know. But there was really red stuff there, like all over the place. And I've been wondering, as you see, that's the mining building, just a part of it. Here in the back is the actual hill with the tower on top. And it's really red. Undeniable red. Maybe that's some part of the dust or whatever there has been when they were doing that. The operation is not ongoing anymore, but we have this also in the rocks itself. So that's a piece of a bigger piece. I was about to saw a piece off in order to put it in the microwave, but turned out that this already fell off due to erosion from the bigger piece. And that's a piece of rock from Outokumpu, not from the mining, it's from part of the older mining area. It looks really nice when it's polished. So I put it in the microwave. You can see there's a whole other bunch of smoke coming out of that. And it's glowing. So there is some metal inside it. Copper. Yeah. It's really stinky. Blue flames. And it's really hot. Can imagine. There's a glowing rock in that. And there's also blue flames burning on that stone. And I put that stone there in order to somehow trying to protect the glass. But since it's really flat, in the meanwhile, I just wanted to show you that once again. That's some quality of copper ore. Yeah, and it's a bit wet, that's why it looks a bit strange. Yeah. I got a bunch of very interesting rocks at home. Now back to the microwave. Because I figured out to push pause whilst doing a video. So I don't have to make 10-minute video of a thing which lasts only a minute. Much less memory space required. Yeah, took me a long time to figure that out. That's glowing, check it out. But that's not the thing yet. Because you will see in a second. As you can see, it's very thin. Just a few millimeters thick. It turned red. It's red. It's much more red than the other stuff. Or like before it has been in the microwave. And I'm still thinking about this connection between sulfur and copper. But this is sulfur. Wikipedia. Characteristics. Sulfur forms several polyatomic molecules. The best known allotrope is octasulfur, cyclo-S8. The point group of cyclo-S8 is D4D and its dipole moment is 0D. Whatever that means. Octosulfur is a soft, bright yellow solid that is odorless, but impure samples have an odor similar to that of matches. Now, as a solid, sulfur is a characteristic lemon yellow. When burned, sulfur melts into a blood red liquid and emits a blue flame. So there is something red. I haven't yet read that far that someone would tell me what's this red stuff called, what it is. But this is even more convincing. Or, yeah. So back to the mine. This time we go like this to the mine. That's from my paper. That's my very first somewhat scientific paper I've ever made. It has a lot of writing issues. Yeah, English is not my mother's tongue. Plate tectonic issues, the influence of electricity in rock forming processes, and the coherent connection between science, mythology, and history of Finland. Sea pinch stone, dragons. And as we know, dragons are electrical features of nature, impersonified into scary animals such as eagles, lions, bears, griffins, unicorns, dragons. These are the plasma rocks, some of the plasma rock pictures. Molten rock on top of molten metal on top of rock. But Outokumpu, copper mine, Oku, which is really red, and it's on the surface conductivity anomaly map, marked explicitly. The old mine is nowadays a museum, but the mining operations there are continuing and probably even expanding. Yeah, and it's another place. I have been there in one of the other mines some years ago, fixing some roof. But anyway, the thing is that here we have molten metal on top of a rock. We have many craters, small and bigger ones, and other very interesting features which almost look like some storm on Jupiter, you know? Craters. Many craters. And now I forgot what I tried to tell you still. Yeah, here for example. Let's go with that. It was here somewhere. Sorry for scrolling around, but yeah, for example here. A ground-to-ground arc discharge, very sketchily, but made by myself. This would imply that there would be some heat, which have not created, or at least morphed the rocks Yes. So now at the bottom of the mine once again, you can see here down, like that's really maybe some 50, 70 meters from the top down, we have this red stuff, which might be this burnt sulfur, which might mean that we really have to take heat into account, and it could be due to the conductivity of copper and stuff that it was just a very, very strong, this kind of lightning bolt. Yeah, for me, it makes sense. We have the surface conductivity anomaly with its shape, which is somewhere, it has the same appearance like the polar cusps in a way, with the polarities and the S shape in the middle and stuff like that. Electrical in nature, totally. Heat could be applied by plasma discharge events. It could burn sulfur. It turns red after it's burned. And now I have proof at the home, like with this microwave stone, which turned really red. So it could be done also with microwaves. Yeah. But anyway, I think I leave it here. This was a very much too long video. Yeah, I'm proud of you if you made it till the end. Thank you. I really appreciate it. Thanks.